Put your hand at the base of your spine right now. Press down gently. You'll feel a small bony point right there. That's not just the end of your spine. That's a tail. Or at least, what's left of one. Every human on Earth is born with the remains of a tail buried inside their body. Most people go their entire lives without knowing it's there. But it raises a question that sounds almost too simple. If we don't need it, why is it still there? And if we used to have one, what happened to it? Here's where it gets strange. Almost every primate on Earth has a tail. Monkeys use theirs to balance, to grip branches, sometimes even to hang upside down. But apes, the group humans belong to, don't. No tail on chimpanzees. No tail on gorillas. No tail on orangutans. And definitely no tail on us. So somewhere in our family tree, one specific ancestor lost something that almost every other primate around it still had. And that change didn't happen by accident. It happened because of one single genetic mistake, millions of years ago, that changed the entire course of primate evolution. Let's rewind about 25 million years. At this point, the ancestors of monkeys and the ancestors of apes were still closely related, and both groups had tails. Tails were useful. They helped with balance while climbing, and for many species living in trees, that mattered constantly. But somewhere around this time, in the ancestors that would eventually become apes, something happened at the genetic level. A tiny error occurred inside a gene responsible for tail development. Scientists eventually gave this gene a name, TBXD. Here's the fascinating part. This wasn't a gene being switched off completely. Researchers discovered something closer to a copy-paste mistake, a small duplicated piece of genetic code landing in the wrong place inside this gene. That one insertion was enough to interrupt how the tail normally forms during development. And once that mutation appeared, it didn't just quietly exist in a few individuals. It spread. Every ape alive today, humans included, carries evidence of this exact same disruption. Which means this wasn't a random coincidence repeating across different species. This was one single mutation, inherited from one common ancestor, that changed the body plan for an entire branch of the primate family tree. But here's the question that actually matters. Why would losing a tail be useful at all? For animals living up in trees, a tail is often essential. It's a built-in counterbalance. But the ancestors of apes weren't just swinging through branches the same way monkeys were. Many researchers believe this line of primates was shifting toward a different kind of movement, using their arms more, hanging and swinging beneath branches instead of running along the tops of them. Without a tail acting as a counterweight for a horizontal running posture, but with strong grasping arms for hanging and swinging, losing the tail may not have been a disadvantage at all. It may have fit perfectly with a completely new way of moving through the environment. This is where the story usually gets simplified into something too clean. People assume evolution deliberately removed the tail because it wasn't needed anymore. But that's not really how evolution works. The mutation happened first. It wasn't planned. It wasn't a response to a need. It was a random genetic accident. What determined whether it stuck around was whether it helped survival afterward. And in this case, it apparently didn't hurt enough to be eliminated. If anything, in a lineage already leaning toward arm-swinging movement, losing the tail lined up well with the direction the body was already heading. But here's the twist scientists are still fascinated by. Losing a tail wasn't a clean, isolated change. In the same genetic study that identified this mutation, researchers found something unexpected. Mice engineered with this exact same mutation didn't just lose their tails. Some of them also developed subtle spinal cord differences. This raises a bigger question that's still being investigated today. Did this ancient mutation only remove a tail, or did it also quietly reshape parts of the human spine and nervous system in ways we're only beginning to understand? Some researchers even suggest the same genetic disruption might be connected to certain spinal birth defects that still appear in humans today, millions of years later. If that connection holds up, it would mean this ancient accident isn't just why you don't have a tail. It might still be shaping human health right now. So the tailbone at the base of your spine isn't just a leftover souvenir from evolution. It's a physical record of one specific genetic accident that rippled forward through millions of years, all the way into the body you're sitting in right now. And that brings us back to the deeper mystery. This wasn't a slow, gradual disappearance. It wasn't tails getting shorter generation after generation until eventually they vanished. It was one sudden genetic interruption that, once it appeared, never left the family tree again. Every ape on the planet carries the exact same genetic scar. Not a similar mutation. Not a comparable one. The same one, inherited from a single common ancestor tens of millions of years ago. Which means the next time you sit down and feel that small bone at the base of your spine, you're not feeling a random evolutionary leftover. You're feeling the exact spot where one accidental copy-paste error in your ancestor's DNA rewrote the body plan for every ape that would ever exist afterward, including you. Scientists still don't fully understand every ripple effect this mutation caused. And that's honestly part of what makes this so compelling. This isn't ancient history that's fully closed. It's an active area of research, with new genetic studies still uncovering connections between the same disruption and modern human development. So here's the real question worth sitting with. If one tiny genetic accident millions of years ago could permanently reshape something as fundamental as the human spine, what other traits we consider normal today might trace back to equally random accidents we haven't discovered yet? What do you think? If that same mutation happened today instead of millions of years ago, do you think it would still spread the same way? Let me know what you think down in the comments.